For lesson 8-2, we're going to start applying our knowledge of proportions and ratios back to geometry. So there's going to be a lot of vocab to make sure you understand. So first of all, what does it mean for two shapes to be similar, and how is this different than two shapes being congruent? So little definition: similar, all angles are congruent and corresponding side lengths are proportional. And when I say all angles are congruent, I really mean all corresponding angles are congruent. So let me draw a little picture. So not great. You'll survive. So I'm trying to say that the angles that are corresponding are exactly the same. So this angle is exactly the same as this angle. If I took a protractor and measured them both, I would get the same number. Another angle set up, and this third angle would match the third angle exactly with a protractor. If one was 27 degrees, the other's 27 degrees. If one's 73 degrees, the other one's 73 degrees. But when I'm talking about corresponding, I'm talking about one in the original picture and one in the new picture. Now, as far as side lengths are proportional, what that means is maybe the first one is A, and the next one is A times some number. And if the bottom one is B, the other bottom one would be times that same number. If the third side was C, C times that same number. That's what it means to be proportional. On the other hand, when I'm talking about congruent, if I talked about congruent things, then all of the side lengths and all of the angles would measure exactly the same. Corresponding angles and side lengths are exactly the same measure. So in addition to the angles being the same, if one side measured 1 inch, the other triangle would have to have a side length of 1 inch. So I don't know that this is going to be perfect, but the idea is that if this is x, then this is x. If this is y, then this is y. If this is z, then this is z. If this angle is 42 degrees, this angle is 42 degrees. If this angle is 67 degrees, this angle is 67 degrees. So similar, they can be different sizes. By the way, congruent polygons are similar, just that the multiplier is 1. So it's kind of a lame similarity. In both of them, the angles have to match up exactly. So another thing we're going to talk about today is a golden rectangle. A golden rectangle is a very, very special kind of rectangle where make sure I get this right, I believe it's 1.618 to 1 is my ratio. It is a special rectangle. It often comes up in real life situations. Just so you know, if you did advanced biology, the golden rectangle comes up a lot. It also comes up in art a lot. It turns out if you survey humans and you say which is the prettiest, they almost always choose something that's this particular proportion. So going back to this definition, it's a special rectangle that produces a rectangle, I should say a similar rectangle when a square is made of its short side. So just as an example, here's the short side. So if I draw a square using that side length, right? So there's my square. My new rectangle is similar to the rectangle that I started with. They're proportional to each other. It's actually really kind of cool. Okay, so you need to understand the 1.618 to 1 for some of the problems. You need to understand similarity. I'm going to go through some other notes. The other notes are actually really important in this particular lesson. I'm going to start with similarity statement. A lot of the problems are going to ask you for a similarity statement. A similarity statement, and it's probably easier to give you an example before I read out the words. So let's say I have two similar triangles. I'm going to make it pretty easy where they're not rotated or flipped around. They just, which by the way is possible. Just they're exactly as is. I'll call this A, B, C, and D, E, and F. So the similarity statement would be A, B, C is similar to D, E, F. The order matters. I'm saying that A became D, B became E, and C became F. This little squiggle right here means similar to. So that is a similarity statement. It's a way of informing the reader of which angles, A, B, and C are the angles. You can also call them vertices. Which vertices correspond between two similar figures. Like I said, the order matters. So I'm going to draw another one. But I'm going to say this one goes there. Maybe this one goes here. And this one goes here. I'm going to stick with my A, B, C, D, E, F. So A, B, C is similar to, in this case the A goes with the F, so I'd have to lift the F first. The B goes with the D, so D would have to come next. And the C goes with the E, so the E would go last. The order has to be the same. The first letter, A, has to correspond with the second letter, F, for all of those. So why do we want a really good similarity statement? Because it makes things really easy. So if I asked you what angle B was the same as, even if I didn't have a picture, I know that B is the second letter on the one side, so it has to go with the one that's the second letter on the other side. The similarity ratio pretty much tells us our answer. If instead I'm talking about proportional, and let's say I said A, C over, and maybe I don't tell you what that is, and then I say BC over, I know that AC is the first and the last, so I need the first and the last. So this one is FE. BC, on the other hand, is the middle and the last, so I need the middle and the last. So this one is DE. Because it tells us what the order of all the letters line up is, that helps us solve our problems. Now for a couple quick examples. So are they similar? If so, give the ratio and the similarity statement. In order to be similar, the angles have to be the same and the sides have to be proportional. So let's kind of show you what that means. This is example 2, by the way, on page 423. So let's see, they said 15, 12, 18, and they called that A, B, C. I'm actually going to pause this so to finish making the drawing, so you can pause it too once you have the drawing showing. For it to be similar, first of all the angles have to match up. I need to be able to match up the angles. So I have one angle there that matches up there. I have an angle here that matches up. And I have an angle here that matches up. So angles check. Excuse me. I also have to show that the corresponding side lengths are proportional. So I need to set up ratios for things that go together. So notice my blue-yellow side is 15. My blue-yellow side here is 20. So I'm going to write the fraction 15 over 20. That's my ratio. I'm going to do the same thing with the other sides that match up. The 12 would go with the 16. And the 18 goes with the 24. I need to reduce my fractions to see if they come out the same. So 15 over 20 is 3/4, 12 over 16 is 3/4, 18 over 24 is also 3/4. So there's the same, which means that they are similar. So A, B, C, similar. A went with F, B went with E, C went with D. There's my similarity statement. And my ratio is 3:4. Maybe in another problem they tell you that two figures are similar. I'm just going to do really easy ones. We're going to say that these are similar. They told us that. And now x, 5, 5, x. No, I don't want that to be x. I want that to be 2. I apologize. And they say, so example, they are similar. Find x. I just need to line up things that go together. The 5 goes to the 2. So the 5 goes to the 2. The x goes to the 5. Once again, those are pretty much your equal signs. So 5 over x equals 2 over 5. Find your extremes. 25 equals 2x. X equals 12.5. For this final example, I'm going to write out a golden ratio problem. So after I have it written, right, it's going to jump and you might want to pause it to write it down. So give me a moment here. So in a golden rectangle problem, the ratio is always the same. It's 1.618 for the long side, 1 for the short side. So if 1.618 becomes 1, 30 centimeters becomes question mark. It's unitless, so it's going to leave it in centimeters. I cross multiply. I get 30 equals 1.618x. And when I divide, x comes out to be about 18.5 centimeters.